So welcome to the final part of nuclear physics internal for level 2, the mass-energy relationship in nuclear reactions. We're going to investigate Einstein's famous equation E equals mc squared. So the famous equation. So in nuclear reactions, the rest mass, the mass when particles are obviously at rest, they're not moving, of the products can be greater or smaller than that of the reactants. And this difference in mass, delta M, is due to the binding energies between the individual particles in the nucleus, and also the fact that the energy and mass are actually equivalent. They're essentially different sides of the same coin. So the equation, which most of you should be familiar with, pretty famous, is E energy equals the change in mass times the speed of light squared. And there we go. So energy, of course, is in joules. The change in mass is the mass in kilograms. C is the speed of light, which we all know is 3 times 10 to the 8 meters per second. And this is the energy that is released, a giant nuclear explosion.
We've all heard of E equals mc squared, but what does it really mean? Einstein's E equals mc squared equation pops up everywhere, from baseball caps to bumper stickers. Heck, it's even the title of a 2008 Mariah Carey album, but don't look to that for an understanding of mass-energy equivalence. In Einstein's equation, E stands for energy and M stands for mass. See, in this, energy and matter are interchangeable. And in this universe, there's a set amount of energy matter. If you've ever read Dr. Seuss's The Sneetches, then you probably know how this works. Remember in the story how the yellow bird characters go through a machine to change back and forth between star-bellied Sneetches and plain-bellied Sneetches. The number of Sneetches remains constant throughout the story, but the ratio between plain and star-bellied changes. It's the same way with energy and matter. The total remains constant, but the ratio changes. Energy regularly changes form into matter and vice versa. This brings us to the c squared portion of the equation, which serves the same purpose as the star-on, star-off machine in the Sneetches. The c stands for the speed of light. So the whole equation breaks down to this. Energy is equal to matter multiplied by the speed of light squared. Why would you need to multiply the matter by the speed of light to produce energy? The reason is that energy, be it light waves or radiation, travels at the speed of light. It breaks down approximately to 186,282 miles per second. Split an atom inside a nuclear power plant or inside an atomic bomb, and the resulting energy releases at the speed of light. But then why is the speed of light squared? The reason here is that kinetic energy is proportional to mass. When you accelerate an object, the kinetic energy increases to the tune of the speed squared. You'll find an example of this in any driver's education manual. If you double your speed, the braking distance is 4 times longer. So the braking distance is equal to the speed squared. The speed of light squared is a colossal number, illustrating just how much energy there is in even tiny amounts of matter. A common example of this is that 1 gram of water contains as much energy as 20,000 tons of exploding TNT. That's why such a small amount of uranium or plutonium can produce such a massive atomic blast. So there you go, energy equals mass times the speed of light squared. Now if you could use this equation and take some sort of small bit of matter and use it to power a starship, what's the weirdest thing you could choose to throw into the engine? I'm thinking either a fluffer nutter or an old NES cartridge. What about you? You can leave a comment below, you can leave a video response, and don't forget to hit that subscribe button so we can keep these videos coming at you.
Right, so we've already looked at Rutherford and his model of the atom. We're now going to look at his work around nuclear physics in terms of transforming one element into another element using the power of the atom. So the first artificial nuclear reaction, which won him his Nobel Prize in 1921, was done by Rutherford, and what he did is he had an atom of nitrogen, he bombarded it with alpha particles, and he got an isotope of oxygen and a proton. And the rest masses are as follows. For nitrogen, it was 23.25 times 10 to the negative 27 kilograms. Helium was 6.65 times 10 to the negative 27 kilograms. The isotope of oxygen was 28.26 times 10 to the negative 27 kilograms. And the proton was 1.67 times 10 to the negative 27 kilograms. So really small numbers. So what I want you to do now, twofold, is show that the mass of the products is greater than that of the reactants, and calculate the energy equivalence of this increase using a certain equation. I'll give you 5 seconds, so pause the video now, and then we'll come back and look at the answer. Right, so welcome back. Let's look at the answer then. So, simply, it's a matter of working out the total mass before, which is the sum of the nitrogen plus the alpha particle, which gives a grand total of 29.895 times 10 to the negative 27 kilograms. The mass arm after of the isotope of oxygen plus the proton gives 29.898 times 10 to the negative 27. So the difference in mass will essentially be the mass after minus the mass before, which gives a really small number of 0.03 times 10 to the negative 27 kilograms. That's the mass increase we have witnessed. So what is this in terms of energy that has been released? Well, we go to our famous equation, E equals delta mc squared, and simply plugging in the numbers, energy equals 0.03 times 10 to the negative 27, that's delta m, times the speed of light squared, giving an answer of 2.7 times 10 to the negative 13 joules for one atom. But of course, in the molecular sense or the atomic sense, we're going to have billions and billions and billions of atoms, so you can imagine the energy that's been released. Right, so the final section is power and nuclear energy. Okay, so I've had a look at nuclear energy previously in the course. Now we're going to calculate the power that's being released by this process. The power of the station, say for example Springfield's nuclear power station, can be calculated using the following formula. Power equals energy divided by time, and rearranging that, energy equals power times time, where P is the power in watts, energy is of course in joules, and time is in seconds. Now, energy in the nuclear energy industry is calculated slightly differently with the units, and the number of electrical units is the power in kilowatts times the time in hours, and the units in terms of electrical units is known as kilowatt hours. This is how we calculate energy in terms of, say, a light bulb. You'll look that it will be in kilowatt hours. So we'll go straight to a question. Let's practice with Homer. So you've got in Springfield, each reactor has a power output of 660 megawatts. Note megawatts. Calculate the cost of using the electricity supplied in 1 hour by one of the reactors at a cost of $0.0289 dollars per unit. Okay, so pause the video now, and we'll come back to the answer in about 5 seconds. Right, so welcome back. So let's now look at the answer and compare your answer with my answer and see if we're on the right track. So if you, from the last slide, you realize that power equals energy divided by time, so you can rearrange that equation using algebra. The energy equals power times time. So now you've converted to megawatts into kilowatts. So you had 660 megawatts, which equals 660 times 10 to the 3 kilowatts, times the 1 hour, because remember energy units of energy is in kilowatt hours, so that means you end up with 660 times 10 to the 3 kilowatt hours. And the cost equals the number of units of energy, which is 660 times 10 to the 3 kilowatt hours, times the cost of 1 unit, which we've been given. So that gives you 660 times 10 to the 3 times 0.0289, which is the cost of 1 unit, to give a grand total of 1.91 times 10 to the 4, or $19,000 for that 1 hour. Quite expensive. Okay, that's excellent. So that's pretty much all you need to know around Einstein's equations. There'll be questions based around that. So all the best for your assessment, and see you for the next unit.